we will start next section for CNN workshop. We talk about CNN concept. Then we will have some Colab experiment on the Google Colab. Remember the first Colab we practiced before is DNN Colab, right? We use MINIS data set. That is a data set used to recognize handwrite digit from 0 to 9. So this is only, recall just help you to memorize all those data set. Okay, so it's 28 by 28 two-dimension data set, grayscale image. And we in the DNN we use fully connected neural network. Okay, we just use one hidden layer and one output layer. Okay, and we get some outcome. And we introduce in the convolution neural network. It should be better for image recognition. Okay, by the convolution. Okay, process to find out the feature. Okay, we generate different feature maps. And also we have another benefit, that is we are using convolution and max pooling to reduce or downsize, okay, the original dimension. So let's see, after this experiment, we can compare to what we used in DNN to see the performance for two different algorithms or machine learning model. So later we will go to the Colab. So we already provide the link you can access. Still, I hope that you can have your own copy. Okay, so you save a copy into your drive, and you can start to modify it. Okay, so this is a very simple code later we will use. So let's first introduce some important parameters first. So let's go back to our slide. So same thing, we will use the Keras and TensorFlow, and so then we use the Keras to construct the convolution neural network. Okay, so the first thing is the input. Okay, the input is again, that's our grayscale images. The second thing is the convolution there. Okay, the convolution, in this example, we will create 3 convolution. Okay, and after convolution, we will have a max pooling layer. Okay, so here is the parameters. So in every convolution in the CNN concept we mentioned, the convolution, the concept is use different filters, okay, to scan the original images and to have a outcome that's called a feature map. Okay, so different filter will generate different images. Okay, so here the first convolution layer we will use 32 different filters, and the filters we have a size that's called kernel size. Okay, and this is so in the when after the convolution scanning process, then we still need a ReLU activation function to generate the nonlinear output. Okay, for the for the nonlinear space. Okay, of this model. And next thing is max pooling. Okay, so we also need a window size. So that's window size 2. So we can find some, CNN concept recall for you. So this is kernel. Okay, so that's a 3x3. Okay, so we use the kernel to scan the original images. So this is the first kernel. We will generate new images. Okay, and if you change the internal of the kernel, it will generate another images. Okay, so that's a convolution part, and the max pooling part is after we generate images. Okay, for example, like this, and we will use max pooling window. Okay, to map. Okay, to map. If this is 2x2, then we will select this area, the maximum value from this 2x2 area. Okay, to put it into a new array. Okay, so that's operation for the max pooling. Okay, so here we have three convolution. Okay, the first 32 filters. Okay, the second 64 filters. The third 128 filters. Okay, and after the first convolution, we have max pooling. Second, we also have a max pooling, but the final one, remember, we need to have a flattened layer that we put all the feature images, okay, into a one-dimensional array. Okay, so if you remember that, this is just a reference illustration. Okay, the image size is different, but actually the concept is the same. We have the convolution to generate convolution feature maps. Then we have the max pooling. Okay, it's every time it will downsize. Every time it will downsize. Okay, and eventually we have a flattened layer. So this is how we construct the convolution network. After the construction, then we can have a model summary. So let's first execute the code in the Colab. So just has a fast go through. So we mentioned about its convolution, okay, and max pooling. Okay, we mentioned about the size, okay, for kernel, and size for max pooling window. Okay, so the final layer is softmax, right? Because it's 10 node to calculate the probability of each value, okay, of each handwritten value. So here we first build the model, and we show some summary of the model, because we want to discuss how we use the convolution and max pooling to downsize, or to try to make the neural network become smaller, the parameter become less. Okay, so this is model output. Let's go back to the slide. We have a more clear image. So here is the outcome we just saw after we run the model summary. Okay, so you can see original we have 28 by 28. After the first convolution is become 26 by 26. So after 3 times of the convolution and 2 times of the max pooling, then we have size originally from 28 to 28 become 3 by 3. Okay, Why? So we can see the convolution will downsize the dimensions based on the equation dimension minus parentheses of kernel size minus tried value. Okay, so you can, if you remember, you can see once we scan the images, okay, so it's because every stride we will generate new images. Okay, so until the kernel hit the very right of the matrix. Okay, so it's so it should minus the stride value. Okay, and so 28 become 26. Okay, so that's how the convolution will try to reduce the dimension. Okay, another example is from 23 and become 11. Okay, so that's how convolution reduce the dimension. And for max pooling, it will reduce based on the equation of the dimension divided by max pooling, the window's height. So you can see the max pooling window when we use 2x2 to scan the 4x2. So every time we will downsize it, just divide by the height of the matrix. So it's well reduced to dimension divided by max. So you can see one example is 26 become 13. So this is how the convolution and max pooling will reduce the dimension. And when we do the model summary, it will also show the parameters. The parameters is very crucial for any machine learning or deep learning model, right? Because if you have too much parameters, you need to learn by gradient descent. Okay, so that's caused a lot of time for the differential calculation, a lot of things, fault point calculation. So the thing is, we want to try to still have the good model, but have less parameters. So you can see this is all the parameters we generate from the model. And how to calculate the parameters, actually, we also provide an equation here. We will not prove the equation, but it's based on a number of filters, which is, you remember in the first layer we have 32, okay? Next layer we have 64, final we have 128, okay? And multiply parentheses of the previous layers filters and multiply the dimension, which is height and width. And +1 is a bias. Remember, activation function inside there is a bias. So this is the equation. So you see there are 320 is just calculate based on the equation. It's 32 filters multiply parentheses of 9 weight +1 bias. So it's become 320. And 18,496 is calculated also by the equation. So that's in this layer we have 64 filters and multiply parentheses of previous layers filters. Okay, and width and height, which is 3x3 of the kernel side, and +1, which is a bias. Okay, so that's how we get parameters. And another thing I want to mention is the kernel. Why we say the kernel, the convolution kernel is also a parameter. So you can see the parameters actually is here, right? That's a 1, 1, 0, 0, 0, 1. That's the thing. Actually, this is also a thing we mentioned about in convolution network. It's exactly like the weight in the neural network. Okay, so every kernel inside of the kernel of a filter the value is exactly like the weight. So it's also the parameter. We have to use the gradient descent algorithm to learn the weight, that is the value in the kernel, okay, to optimize the feature maps. Okay, so that's why it's also called the parameters. In every element in the kernel is also a parameter as a weight in the neural network. So that's a model we generate. Actually, this is all the parameters. It's around 100K. It's around 100K. Okay, so that's a model we generate. Later, we can put all the training images and the test images into the model, just like what we did in the DNN workshop. So we go to the code. So the same thing, the minute we will separate chain images data portion and test image data portion, okay? And we also will use the reshape to become one dimension and use normalization, that the value in between 0 to 1. And to model compile, I think we introduced in the DNN workshop, okay, we specify loss function as cross entropy, okay, and some parameters, the same, we use batch size 128, we separate validation from the chaining, use 20%, and apex file. So here we can do the chaining, okay, then in the last part, we will use the test data set to evaluate the model. Okay, we will just first use the accuracy for evaluation. So let's run the code. And it will take some time. So while it's training, let's discuss something else. Back to the slide. So after the evaluation, later, we first tell you the outcome first. Okay, then we go back to the the code to see the proof. So let's guess. Well, it's matched. So the conclusion. So after we run the final part of the code, we will evaluate test data set, and in the end, that should be higher than the DNN because we have the feature map, right? The feature map will help us to learn the feature of the images. Okay, so should be higher. Okay, should be higher. In my previous test, that will become around 99 something compared to DNN's 97 something. Okay, but I want to say that use DNN, you can still get 99 something by tuning. Okay, for example, in the workshop, if you remember, we only use one hidden layer, one layer, one neural network in the hidden layer. Actually, we can add multiple layers in the hidden layer. Okay, so there are a lot of ways we can do, but the thing is, the most important thing is we mentioned about the parameter size. Okay, because that's matter. Okay, we don't want to consume too much power, right? Especially if we train it in a very powerful machine, we have a lot of parameters. That should be fine. But remember, this course is the next portion of this course is edge computing. That is, we will put the chain model into a smaller or tiny devices. So at that time, we don't like the parameters. We don't like too many parameters, right? So we might not have enough computing powers. So use a very high accuracy model, but has less parameters. Is very important, especially for edge computing. So we can see a comparison by using a DNN just one layer. We used the 512 node in the hidden layer, and so the parameters should, and you should plus bias and other parameters. So you multiply 28 by 28 by 512 should be around 40K. Okay, should be around 40K. But we just calculate the parameters. If you make a summation, it's around 10K. It's around 10K. So we use convolution neural network. We might have a higher accuracy, but at the same time to reduce the parameters. So let's go back to see the training outcomes. Okay, so this is luckily I'm not wrong. Okay, it's 0.99. Okay, so that's why we use convolution neural network for image recognition, and we have already see the proof of the performance. Let's go back to our slide, okay, to have some summary. So this is a very basic part of the deep learning neural network. If you want to learn more things, here I provide 2 resources for you on Google. It's free course. So I will here to have a fast go through for you. So the first free course series on Google is Google Machine Learning. So you can see here. So the Google Machine Learning provide 2 portions. The first portion is fundamental foundation courses. Okay, so here we have a 6 part. Okay, and very important, if you want to dive into, you can go to the machine learning crash course. Okay, the machine learning crash course provide 25 lessons. Okay, of the just of different topic in machine learning. So you can just start the 25 courses. Okay, so each courses, some of the course provide a video introduction. Okay, so one thing on the Google's website for deep learning, I think that's very funny or interesting is you can have a emulation tool. Okay, emulation tool for the for your practice. For example, you just click the neural network and playground, and here it provide a emulation tool. Okay, this emulation tool is quite, it's quite easy for you. Its final outcome is you want to classify 2 colors, right? The blue one and the orange one. Okay, so here you have 2 variables, x1 and x2. Then there are a lot of parameters in we learned in the neural network or deep learning. We can start to input, for example, the learning rate. Okay, you can have a smaller learning rate. Okay, and you can have a different activation function, just like we mentioned about Sycamore and ReLU. Okay, and there are other regulations which to prevent the overfitting. You can specify. We have L2 and L1. Okay, And here we have other things just like how many training data we want to use. That's for training data set, okay? And the batch size, okay? We also can adjust, okay? The very powerful part is you can add in every layer you can specify a neuron you want to add, and you can have more layers, okay? You can have fully connected neural network or partial connected. And then you can start the chaining to see the loss function, okay, to see your outcome, okay. So that's a very good thing to start to learn the machine learning. Actually, a lot of concepts just like how to separate different data set, the training set, the validation set, okay. So very good stuff for you to reference. So that's first resource want to introduce to you. And the next thing is on some advanced portion. So, for example, we just mentioned we have on Google we have a foundational course. We also have an advanced course. Okay, in the advanced course, if not just to learn deep learning, if you want to learn more on machine learning, so there are other algorithms also very useful for structural data, just like decision forest, decision tree, and clustering for unsupervised learning. And today I want to also help you to go further if you want to just not only use the MNIST data set to do the training. Actually, you want to do training and use other data sets. So it's a very famous one is how to recognize dog and cat. So in the advanced course on Google side, here is the example help you to the data set you can download, and here provide three exercises. The three exercises are pretty good. Help you to build a convolution neural network to recognize cat and dogs. Okay. Also, it's provide online Colab for you. Okay. You can just launch the exercise. Okay. And then most important part in the deep learning or machine learning is we always fighting with the overfitting problem. That is when you train a data set, you train more time, but that's useless, okay, because you focus too much on the training data set, so you cannot get a good outcome. That's happened a lot. So how to overcome the overfitting? Then we have a different way to do that. So in the advanced course, it provides several guidance on how to conquer the overfitting problem. Okay, for example, one thing is do the data argumentation. So if you have a dog, then you just use different angles. Okay, so it can learn different features. So this is one way to prevent overfitting. So another thing is drop out. Okay, so that's when you do the training, you randomly drop some of the nodes, so it's forget what it learned before, because if it remember means it's still in the overfitting. So we randomly drop some of the node to do the new training. So there are several ways we can do the tuning. But we need a very concrete data set. So the Google dog and cat recognition exercise is pretty good. So I recommend to go further. You can have some time to see the foundational course, and to see have a review and also do some experiment on the advanced courses. Okay, so that's a section today.